Welcome back to Physics Junction. In today's video, let me talk about the coastal nanostructure. Let me start with a brief introduction to coastal nanostructure. This is the schematic representation of a coastal structure. This is the inner part, so this is called core. The outer layer is known as the shell material. Both the core and the shell material are at the nanoscale. Why do we prefer coastal nanostructures? Coastal nanostructures are mostly designed to improve the stability of the colloid particles. The colloid particles are nothing but dispersion of solid nanoparticles into a liquid. But due to the gravity or centrifugal motion, these solid particles try to settle down at the bottom of the liquid. Sometimes nanoparticle coagulation occurs. These all affect strongly the stability of the colloid particle. So to improve the stability of the colloid particle, some kind of surfactant is needed, that is the shell material, which improves the individual particle separation. So to enhance the stability of the technologically important materials, the coastal structures are preferred. Therefore, a coastal nanostructure is composed of two or more nanostructured material, out of which one material is at the center. So that is called core. The other material is the outer layer which is around the core. So that is called the shell material. Here the shell acts as encapsulation for the core material, and the core and shell materials are made up of two different materials. So it's called the biphasic nanomaterial. Now let's talk about core material in detail. Core is a multifunctional component. It can have any dimensional from 0 to 3-dimensional. It may be 0-dimensional, 1-dimensional, 2-dimensional or 3-dimensional material. Coating the core material with the shell material or with the surfactant modifies the thermal stability and the reactivity of the core surface. Thus, it improves the stability or the dispersibility of the core particle, as well the encapsulation of the core material by the surfactant makes the core material remains in unaggregated form. The next one is the shell material. It's an outer layer which has a controllable thickness from angstrom to micrometer scale. Usually the shell material acts as a physical barrier between the optically active core and the surrounding medium, and it makes the core material less sensitive to the environmental hazards, surface chemistry and photooxidation. Basically, it helps to improve the property of the core material. Next one is very important characteristics, that is suppression of surface electronic trap states. In quantum dot based optoelectronic devices, surface electronic trap states induces the non-radiative recombination, which strongly affects the fluorescence quantum yield. But with the shell material, one can suppress the surface electronic trap states, which gives rise to strongly enhanced fluorescence quantum yield. As well, coating the core material with a layer of shell material, it provides the surface chemistry. That means so one can have a precise control over tailoring the surface properties of the core material. So thus it modifies the functionalization of the nanoparticles. So this is the coastal nanostructure. Therefore, the coastal nanostructure is defined as concentric multilayer nanoparticles with the improved properties. Now we are going to see different types of coastal structure depending upon the composition and arrangements of two components in the coastal material. They are classified into many types. So based on the material type, they are classified as inorganic core, inorganic shell, inorganic core, organic shell, organic core, inorganic shell, and organic core, organic shell. Based on this classification, the coastal materials can have the combination of metal core, different metal shell, metal core, non-metal shell, metal core, polymer shell, polymer core, non-metal shell, polymer core, different polymer shell. These are the different combinations of coastal structures. The next one is the morphology of the core particles. So the core particles can have any kind of morphology. It's like a spherical, double core, polyhedral, porous core, hollow core with a single shell, hollow core with a double shell, movable core, multi-core, coastal nanoparticles with a irregular shape, then nanorod. These are the different morphologies of the core particles. So different morphologies of the core particles are coated with a thin layer of shell material to get a desired morphology in the coastal structures. Also, the interaction between the core and the shell material determine the new properties of the coastal structure. Next one is the properties of coastal structure. Because of their unique characteristics like diverse composition, various morphologies, controllable particle size, and synergistic effect among the components, the coastal particles exhibit enhanced optical and catalytic properties. Specifically in colloidal particle system, it modifies the surface chemical and thus the coastal nanostructures show enhanced properties compared to the non-functionalized uncoated particles. Also, by changing the elemental constituents, their structural and optical properties can be tuned. The interaction between the core and the shell allows the possibility of greater spectral tunability from the ultraviolet region through visible to near infrared region. Then selection of shell material. The selection of cell material is greatly depends on for what application the coastal structure is going to be used. Based on that, the shell material is selected. This is the continuation of properties of coastal particles. The coastal nanostructures are highly functional materials with enhanced properties, and these materials have multifunctional and synergistic physiochemical properties depending on the choice of the two components. In some cases, the coastal particles possess the properties both from core and shell material. In some cases, it differs from the intrinsic properties of both the materials. Thus, the coastal functional materials with novel properties can be obtained by having fine control over the chemical composition, dimension, and geometries of the coastal material. So now let's move on to various synthesis approaches for the preparation of coastal nanoparticles. With related to the type of core and shell materials and the synthesis techniques, the properties of the coastal structure is modified. The different approaches for the preparation of coastal nanostructure are hydrothermal synthesis, solvothermal synthesis, Sol-Gel method, emulsion polymerization, and microemulsion polymerization. The coastal nanostructure synthesis is a two-step process. One is the synthesis of core, the second one is the synthesis of the shell material. So during the synthesis time, the core particles are separately synthesized, which is undergone some proper surface modification. After that, the shell material with the desired thickness is coated on the core particle. Now let's see the formation of coastal silica particles by the by layer approach. So we have a solid microsphere, which is a negatively charged silica core particle, and this negatively charged silica particles are coated with polymer layer, which is a positively charged shell material. This is the first step. Here the polymer selected is polyelectrolyte. The next step is immersion of polymer coated silica particle into a dispersion of oppositely charged nanosphere. So now we have a core particle with a double layer. So one is the polymer coating, another one is the oppositely charged nanoparticle layer, and this whole process is repeated, that is immersion into the polymer solution and the oppositely charged nanosphere dispersion until the desired shell thickness is obtained. So this is the formation of coastal silica particles by the layer approach. So next one is the synthesis of silica cores by the Stauber method. Stauber method is a chemical process which is used for the preparation of uniform sized silica core particles. It involves two steps. One is the hydrolysis of tetraethyl orthosilicate into silanol monomer and the subsequent condensation of silanol monomer into siloxane network in the presence of alcoholic medium. Here the ammonium hydroxide is used as a morphological catalyst. Also, the particles with 50 nanometer to 1 micrometer can be obtained by varying the relative concentration of tetraethyl orthosilicate. So here the picture shows the synthesis of silica cores by Stauber method. So the first one is the silica core material, that is a non-porous silica core material, and the second one is the porous silica core particle. After the removal of surfactant, it shows the porosity. So then let's move on to properties of silica core particle. Because of larger surface area, higher functionality, good biocompatibility and biodegradability, and good monodispersity, and its stability against coagulation, chemical inertness, optical transparency, all these makes silica as a widely used material to form the coastal nanostructure. Now let's see various challenges in the preparation of coastal nanostructure. First one is the agglomeration of the core particles. Agglomeration occurs due to the adhesion of the particles to each other in the reaction media. So to avoid the agglomeration, the pH of the solution should be maintained, as well the suitable surfactant material should be used. The other challenges are incomplete coverage of the core surface and having control over the reaction rate. A very important challenge is the preferential formation of the separate particles of shell material. That is, the shell material tries to grow as a separate particle rather than coating the core. This can be eliminated by using the bottom-up approach, which helps to get a uniform layer of shell thickness. Sometimes hybrid approach is used, that is, for the preparation of the core material top down approach is used, and for the preparation of the shell material with the desired thickness the bottom up approach is used. These are the challenges in the preparation of the coastal nanostructures. Here we have an example for a silica at gold shell coastal nanostructure. So the first one represents the silica core, and this is the growth of metal shells on the silica cores by the deposited metal nanoparticles. The second one represents the reduction of metal species accompanied by the precipitation of metal nanoparticles on the modified silica core. Here the substantial mechanical and thermal stability of the core particle combined with the significant electric, optic and catalytic properties of the noble metal nanoparticles and provide unique characteristics to the coastal nanostructure. So here we have the extinction spectra of silica at gold nanocomposite. The diameter of the silica core is 60 nanometer and gold shell thickness is 20 nanometer. Here the thickness varies from 20 nanometer to 5 nanometer. This is the coastal structure with the 5 nanometer shell thickness. Here it represents the optical resonances of various sizes of silica at gold coastal nanostructure as a function of their shell thickness, and it shows the changes in surface plasma and resonance position. The optical resonance peak of the coastal structure with the 20 nanometer shell thickness is around 750 nanometer, where the shell thickness is 5 nanometer. It shows the optical resonance at 1015 nanometer. So with respect to the shell thickness, it shows the redshift in the SPR peak position. So now let's move on to coastal plasmonic nanostructure. From the previous slide, we understand coastal nanostructure allows to tune the plasmonic resonance in a wide range of wavelength. Here we have few more examples for the coastal plasmonic nanostructures, that is metal core with a dielectric shell and dielectric core with a metallic shell. Here the various metal core used are made from noble plasmonic metal such as gold, silver and copper, with the shapes that include nanosphere, triangles, cubes, prisms and nanorods. And these metal nanoparticles show significant impacts on the optical and fluorescent emission properties with the optically active insulating shell material. Here the picture represents the metal core, dielectric shell and coastal nanostructure. So here epsilon 1 and epsilon 2 are the permittivity of core and shell material. The different plasmonic coastal nanostructure applications are listed here: solar cell, sensing, surface enhanced Raman spectroscopy, photothermal ablation, drug delivery, and photocatalysis. Now we are going to see the plasmonic resonant modes of coastal plasmonic structure. Let's take the example of metal core and a dielectric shell. So in this case, the plasmonic oscillation of metal nanoparticles interact with the polarization charge oscillation of the dielectric material under the irradiation of light through Coulombic interaction. So the dielectric shell transfer the energy to free electrons of the metal nanoparticles and giving rise to the enhanced plasmonic resonance. So with the metal core and a dielectric shell, the metal nanoparticles are embedded in the high refractive index material. So it creates the single plasmonic dipole mode. But with the case of dielectric core metal shell, the dielectric material is embedded in the metal shell. So here it creates the two plasmonic resonant modes, and the frequency of the plasmonic resonance strongly depends on the shell thickness. The next one is plasmonic metal semiconductor coastal nanostructure, that is metal core and semiconductor shell nanostructure. When the metal nanoparticles interact with the lights of suitable frequency, the electron density of metal nanoparticle begins to oscillate at the frequency of the light, that is called the surface plasmon resonance effect. So the proximity of the metal nanoparticle strongly influence the optical properties of the semiconductor nanostructure. So the SPR effect enables the injection of hot electrons generated from the metal nanoparticles into the nearby semiconductor, thus expanding the light absorption ability of the semiconductor nanostructure. Also, when the metal nanoparticle interacts with the light, an electromagnetic field is created around the metal nanoparticle, which accelerates the electron hole separation and increasing the light scattering for the reuse of unabsorbed light. Here we are going to see the photocatalytic performance of AU metal at a TiO2 semiconductor quotient nanostructure. The presence of AU metal nanoparticles expand the light absorption and accelerates the electron hole separation, thus improves the photocatalytic efficiency of the AU at TiO2 quotient nanosystem. Here AU particles with different morphologies such as nanorods, nanocubes and nanosphere are prepared initially. Then the TiO2 shell material with a uniform thickness is coated on it. The impact of thickness and crystallinity of the TiO2 shell material as well the several morphologies of the AU core particles on photocatalytic performance of AU and TiO2 quotient structure have been investigated with the degradation of methylene blue, and it shows an excellent performance with the plasma-mediated photocatalysis. Now let's see few examples for polymer-based quotient nanostructure. First one is the polymer semiconductor quotient nanostructure. Here ZNO semiconductor core particle which is deposited with the polymer layer, and this process is carried out via the oxidative polymerization of phenol, which greatly improves the electron hole separation in ZNO photocatalyst. Also, we have some applications of polymer semiconductor quotient nanostructure. First one is organic light emitting diodes, organic photovoltaics, sensors, and organic field effect transistors. Next one is polymer core, polymer shell nanostructure. Hand et al. Research group synthesized polyaniline coated polybutyl methacrylate quotient nanostructure, which is formulated into electrically conductive colloidal ink that is appropriate for use in roll-to-roll printing. This picture shows the schematic representation of preparation of polymer quotient nanostructure. This is the structure of butyl methacrylate, and the solid sphere represents the mono-dispersed polybutyl methacrylate with a diameter of 200 nanometer, and this particle is coated with polyaniline. This process is known as emulsion polymerization process. The next step is adsorption of PVP onto the core particles. PVP is used for stabilization of polymer material, and the resulting quotient particles were purified by the centrifuge process, and this is the example for preparation of polymer core, polymer shell nanostructure. So far we discussed a lot on fundamentals of quotient nanostructures, synthesis and properties. I hope you might have some good idea about quotient nanostructures now. If you have any questions, please let me know. Here I have listed the references, and thanks for watching.